BFR in fully reusable configuration, without any orbital refueling, we expect to have a payload capability of 150 tons to low Earth orbit. BFR, you can get a sense of scale by looking at the tiny person there. It's really quite a big vehicle. Main body diameter is about 9 meters or 30 feet. And it consists of, the booster is lifted by 31 Raptor engines that produce a thrust of about 5,400 tons, lifting a 4,400 ton vehicle straight up. Just the basics about the ship: 48-meter length. Dry mass we're expecting to be about 85 tons. Technically, our design says 75 tons, but inevitably there's mass growth. And that ship will contain 1,100 tons of propellant with a design of an ascent design of 150 tons and a return mass of 50. So you can think of this as essentially combining the upper stage of the rocket with Dragon. It's like your Falcon 9 upper stage and Dragon were combined. So as I'll go into each of these items in detail, but you've got obviously the engine section on the rear, the propellant tanks in the middle, and then a large payload bay in the front. So the cargo area has a pressurized volume of 825 cubic meters. This also is greater than the pressurized area of an A380. So really is capable of carrying a tremendous amount of payload. In a Mars transit configuration, since you'd be taking 3 months in a really good scenario, but maybe as much as 6 months, some number of months, single-digit months, this is where the propellant is located. And this is subcooled methane and oxygen. So the ship engine section consists of four vacuum Raptor engines and 2 sea-level engines. So all 6 engines are capable of gimbaling. The engines with the high expansion ratio have a relatively smaller gimbal area or gimbal range and a slower gimbal rate. The 2 center engines have a very high gimbal range and can gimbal very quickly. And you can land the ship with either one of the 2 center engines. And then for refilling, where you just saw, the two ships would actually mate at the rear section. They would use the same mating interface that they used to connect to the booster on liftoff. This gives you sort of a rough sense of rocket capability, starting off at the low end with the Falcon 1 at a half ton, and then going up to BFR at 150. So I think it's important to note that BFR has more capability than Saturn V, even with full reusability. Based on the calculations we've done, we can actually do lunar surface missions with no propellant production on the surface of the moon. So if we do a high elliptic parking orbit for the ship and retank in a high elliptic orbit, we can go all the way to the moon and back with no local propellant production on the moon. So I think that would enable the creation of moon base alpha or some sort of lunar base. And it's the same approach that I mentioned before, which is you send the spaceship up to orbit, you retank it or refill it until it has full tanks, and it travels to Mars, lands on Mars. For Mars, you will need local propellant production. But Mars has a CO2 atmosphere and plenty of water ice. That gives you CO2 and H2O, so you can make, therefore, CH4 and O2. So you come in, you're entering very quickly, going 7.5 kilometers a second. For Mars, there will be some ablation of the heat shield. So it's just like a sort of brake pad wearing away. It is a multi-use heat shield, but unlike for Earth operations, it's coming in hot enough that you will see some wear of the heat shield. But because Mars has an atmosphere, albeit not a particularly dense one, you can remove almost all the energy aerodynamically. And we've proven out supersonic retropropulsion many times with Falcon 9, so we feel very comfortable about that. This is because it's sort of, you can see it's sort of a mesh system. It's not meant to be sort of particularly pretty because it's just trying to simulate the physics of it. But the size of the cone gives you a rough approximation for how much thrust the engines are producing. That's not a typo. Although it is aspirational. There were two cargo and two crew. The goal of these initial missions is to find the best source of water. That's for the first mission. And then the second mission, the goal is to build the propellant plant. And build up the base, starting obviously with one ship, then multiple ships, then start building out the city, then making the city bigger, even bigger. Traveling at 27,000 kilometers an hour, or roughly 18,000 miles an hour. This is where the propulsive landing becomes very important to get it right. So most of what people consider to be long-distance trips would be completed in less than half an hour.